All right, so we are going to start today talking about a new topic.
Great. That makes me happy.
And in fact, we're going to go ahead and make this will be a new unit. I mean, Wendy started me. I'm going to call this Unit 3.
Are you recording?
I am recording. Thank you for asking. Okay, so we're starting today is a new topic called implicit differentiation. Okay, this is a really important technique in calculus. This is another example. This is a good day in calculus. This is one where we get to harness some stuff that we already know and just apply it to a different topic, and it expands our abilities to do problems without really having to learn a lot of new stuff. Right, so this is ultimately going to lead us to a really cool applied topic in calculus called related rates. And that's one of the times when you really get to see why calculus is so much more powerful than pre-calculus. This is one of the first opportunities to see, wow, okay, this is stuff you could have not even begun to think about in pre-calculus, but now in calculus it gets pretty easy. And they're much more, like if you look at the kinds of problems you deal with in physics and in science and engineering, they inherently, anything that's interesting requires calculus because it's talking about a dynamic system, something that's changing with time, not something that's static, right? And so here we're going to start to see that a little bit here pretty quick when we move into the topic of related rates. Okay, but implicit differentiation. So first of all, here's just an example of a problem that we're not going to do today, but we'll come back and do later. Okay, but we really can't do right now. We could, but it's just not natural for you to think about. But after today, it will be. So what about this? This is an actual physiology problem that we could tackle using calculus. The speed s of blood that is r centimeters from the center of an artery is given by this equation. Okay, s equals c times capital R squared minus small r squared, where c is some constant, capital R is the radius of the artery, s is the speed of the blood measured in centimeters per second, and little r, remember, is just telling us how far are we from the center of the artery, right? So if I were to look at it like a cross section of an artery, we got this artery, and here's the cross section of the artery. And from the center of the artery, that little distance right there would just be r. How far are we from the exact center of the artery? Okay. Now we can approximate this. An easy way to understand this is the idea of laminar flow. Remember, I did not talk with you about that the other day. Okay. Where you just got layers of flow through a pipe or an artery, where the layer next to the artery is going to move the slowest because it's interacting with the wall of the artery. It's getting slowed down by the friction of the artery. Then the next layer inside that's going to move a little faster, but it's interacting with the slow layer of blood, so it gets slowed down. Ultimately, the one that goes the fastest is that one little bit of, that little core of blood flow through the exact center that's the furthest possible away from the wall of the artery. Yeah.
So if our layers are getting infinitely smaller, right? Mm-hmm. Then the one in the very center could go like infinitely fast.
No, it's not going to go infinitely fast. It's not going to go infinitely fast, but it goes faster. And you can't really. Well,
until you get down to the molecules, I guess.
Right. But even if you did,
even the smallest layer is going to be one chain of molecules.
Sure. But even then, the suggestion here, I think, is that if you didn't have finite-sized molecules that would go infinitely fast, it wouldn't go infinitely fast even if there was no friction, right? Like you can do, if you take a superfluid traveling through a vessel, like liquid helium-4 or something that has no viscosity, it doesn't go infinitely fast. It just goes faster than a viscous fluid. Okay, so it still doesn't. There's no reason to go infinitely fast, but it just goes faster in the center. Okay. So now what happens here? So here's the situation we've got. Suppose a drug is administered and the artery begins to dilate. So we got a vasodilator going on here, right? What's that mean if it dilates? It's going to expand, right? So the artery is going to dilate and expand. at a rate of dr dt. Remember, capital R is the radius of the artery, so that's changing now at a rate dr dt. Doesn't that make sense? Dr dt is going to be the rate of change of radius with respect to time. So the units would be something like centimeters per second. Okay. At a constant distance r, as the vessel dilates, find the rate at which the speed changes, right? And if you just pause and just really contemplate this for a second. If the artery is getting bigger, then at some fixed radius, that point in the vessel is going to end up being further from the wall of the vessel, and so you'd expect the blood flow to increase its speed at that point, right? So we're trying to, using calculus, we're going to try to come up with an amount. We're going to try to quantify that. Now, well, what is the rate at which the speed is increasing? You can see that this would clearly be a number that if you were studying vascular flow, this would be an important thing to know, maybe, right? When you're let's say you're a drug manufacturer and you're studying the effects of this vasodilator for coronary patients or something, or people that have heart disease. This would be an important thing to know, right? Okay, so we'll come back to that. We'll come back to that. And what we want to do now, I'm going to show you just a couple problems. Do you have an idea how we could do this? Because this is the kind of stuff we're going to do today. What if I have a function z equals x times y? So this isn't a function of a single variable. This is a function of two variables. We have z's and x's and y. What if I wanted to calculate dz dt? Does that seem a little weird? Okay, I mean, I'm not taking the derivative of z with respect to x or y. I'm taking it with respect to t. Time, let's say. Okay, we'll come back to that one too. That's not that hard, but it seems weird now. So now we're going to look at something more traditional. We can all do this. What if I give you the equation y equals x squared, and I want to find the tangent line when x equals 3? Good review. We've done problems like this many times. So if I want to come up with the equation of the tangent line, what do I need? Okay, so I need the derivative, and the purpose of the derivative is going to be to find what?
The tangent.
What about the tangent line? Slope of the tangent line. Okay, good. So we need a y prime, don't we? So what is y prime?
2x.
Okay, so then when x equals 3, what's y prime going to equal? 6. Okay, and then to find the tangent line, I've got a slope. What else do I need? Point. Okay, so what's the value of y when x equals 3? 9. So then we've got the point 3, 9, and the slope of the tangent line is 6. Point slope, and we're done, right? So y minus 9 equals 6 times the quantity x minus 3, done. There's my line. No big deal, okay? How about that one?
Which
A little tougher.
take
How about that one? I mean, we're going to come up with some different ways of approaching this.
Can you take x prime?
What's x prime?
Be the derivative of y is right.
Okay, x prime, I mean, you're onto something here maybe,
But like,
but what are you,
is it a tangent line when it's x prime? Like the slope of the tangent line when it's x prime?
okay, so, I mean, x prime is ill-defined at this point.
Yeah.
Y prime is dy dx, you're suggesting x prime is what?
dx dt.
Dx dy maybe? So the answer is, yes, you could do that. That would be something you could do, but we don't necessarily even have to. Okay, but that's not a bad idea. I mean, that really is a pretty good idea. We'll come back and, I know I always say this, we'll come back and we'll look at that approach soon. When we're gonna eventually here in the fairly near future, we'll talk about finding derivatives of inverses without actually having to explicitly calculate the inverse of a function. There's some tricks we can do, but that's later. That's later. There is something else we can do, but we could even do this traditionally, right? if I want to find, we did an example a second ago where in order to find the equation of the tangent line, we just needed to calculate y prime at that point, right? To get the slope of the tangent line, and then I need a point. Well, we could sort of do the same thing here, right? But the problem is I've got a y squared instead of a y. So what, okay, so I could solve for y maybe, right? I could square root both sides, and then what am I going to get? Y equals
Square root of x.
plus or minus, right? Plus or minus. Plus or minus the square root of x. Okay? Now, why am I getting a plus or minus there? Like if I were to graph this thing, if I go back to the previous example and I graph this, what's that look like? I've got my xy plane. The graph of y equals x squared is pretty straightforward and simple. That's just a parabola. And then I've got a point out here with coordinates 3, 9, so over 3, up 9. And I've got a tangent line right there that has a slope of 6. Right? No big deal. What about this one though?
Because you can't,
If I graph the relation y squared equals x, what does that look like?
it doesn't allow the
It just looks
other
that
half.
way.
Ah, okay, it's a sideways parabola, isn't it?
Yeah.
Okay. And there's a couple ways we can get to to knowing that. So that it's a sideways parabola, how come? Somebody, raise your hands here, somebody give me a justification for how do I know that's a sideways parabola, and what's one way?
Because the inverse is just reflection over x equals 1.
Ah, good, okay, so you remembered that, that's good, we talked about that, right? So this is just the inverse, everybody agree this is the inverse of y equals x squared? Because what's it mean to be an inverse relation? You're swapping the domain and the range, so you're exchanging the x's and the y's, right? So if this is an inverse, it's just going to be a reflection of the parabola y equals x squared over the line y equals x. Remember the two steps to getting that without having to reflect over a non-vertical or horizontal line? Remember we rotate 90 degrees counterclockwise and then reflect over the y-axis. Okay, either way we're going to get this, aren't we? Right?
Yeah.
Either way we're going to get this. We're going to get that parabola. Okay. Okay, why did the math gods don't do anything accidentally. Everything has a purpose. Why did they give us the plus or minus there? What do you think?
Because the sideways parabola isn't a function because for the values of x, there's more than one value.
Okay, it violates the vertical line test, doesn't it? Right? Violates the vertical line test. So the math gods, in their infinite wisdom, they gave us two separate functions. They gave us the plus square root of x, which looks like this one, right? And they gave us, you like my use of the Christmas colors? They gave us the minus square root, which is the bottom one, right? Everybody agree? The negative square root. So taken one at a time, those are two functions, agree? Everybody with me?
Yeah.
Okay, so then, really, when I say find the tangent line probably isn't grammatically correct. How many tangent lines am I going to get when y equals, actually I should say, I don't want to say when y equals 9, I want to say when x equals, it should be when x equals 9.
We'll have to-
Yeah, I got to change that. So that's supposed to be when x equals 9, not y. I'm going to get two, aren't I? We can already see that. I'm going to get one of them up here, right? And I'm going to get one of them down here. Right? But I'm only going to get one tangent line per function. Okay? So I could just split this up into two parts, couldn't I?
Yeah.
I could just deal with both of these individually, right? This is starting to be more of a problem than the other one, though, isn't it? It's a little tougher. Seems like it. So we've got the one y equals the square root of x, and y equals negative the square root of x, right? Each of those we can differentiate, and we can do it just traditionally like we did before. So if I differentiate, let's do the green one first. What's the derivative?
1
1
times
times
negative.
so negative.
So I get 1/2 x to the negative 1/2?
Yes.
If I write that with square roots,
You equal it.
1 over, I got 2 on the bottom, and then x to the negative 1/2 is the square root on the bottom. Everybody agree? Okay. How about the red one? That's y prime. Isn't it? If I calculate y prime for the red graph, same thing, but I've just got a minus out front, right?
Uh-huh.
So I'm getting a negative 1 over 2 radical x. Okay? And at x equals 9, what's that giving me? So at x equals 9, y prime equals what?
Yes.
1 over 6?
Mhm.
Okay? And if I plug 9 into my function, I get the point 9, 3. Okay? How about over here? I'm getting y prime equals just negative 1 to 6. And I've got the point 9, negative 3.
Yes.
Okay? That works, doesn't it? I mean, that matches my graph, right? Everybody agree? Okay? All right. Now I got a challenge for you. Could we have
So right.
I gotta fix that here. There we go. So here's my challenge. Could I have done that without having to split that into two separate functions? The process that we did there is called an explicit process. Because what was our strategy? In order for us to calculate dy dx, we reasoned that we first have to solve for y, right? Once I solve for y and get y by itself, then I can calculate dy dx by just differentiating, okay? So that's an explicit process if I have to explicitly solve for y first and then differentiate, okay? That's the only way we've ever done derivatives. It's the only technique we've ever really needed up to this point. But now we want to see if we can do this in a different way. Could I have somehow done this without having to ever break this into two separate functions? Could I have just done a single derivative? And in order to see that, I want you to see if you can combine both of these together to form an answer that's a green answer and a red answer that are the same. Okay, and I'll give you a little hint, just in the order of interest of speeding things up a little bit. Can I define the derivative recursively? Remember doing recursive stuff last year in pre-calculus? Recursive processes in math are just like a dog chasing its tail. So you're gonna try to write the answer in terms of the original problem. Could we write this using a y maybe instead of an x? What is y equal to in the green instance? Square root of x, right? Okay. Everybody agree? So I could write this as y prime equals 1 over 2 y. Everybody agree? Now, what about the red one? Okay, the red one, I've got the negative sign in kind of an awkward place here, but really, the negative sign doesn't have to be out front.
No.
The negative sign could be attached to any one of these three factors, couldn't it?
Yeah.
So what if we attached it to the square root of x? What if I instead rewrote this as y prime equals 1 over 2 times negative radical x? Same thing, agreed? Algebraically. Well, doesn't that give me back, look, y prime equals 1 over 2y?
That's crazy.
Okay, so now the question is, could I somehow have gotten from my original starting place, which you remember was the relation y squared equals x over to y equals 1 over 2y, without having to go through all that huge process. And here's my hint. You're really just applying the chain rule. Any suggestions? Let's try, oh, okay.
We just did.
Yeah, so I guess I forgot I had done, I built this a few days ago. So that's where I meant to do everything we just did. Had it all set up and everything. Okay, but what about right here? So we want to see if we can get to a place where we're getting y prime equals 1 over 2y. What if we just differentiate with respect to x, both sides of the equation? That should be okay to do, right? Because I've got an equation, the left side and the right side are equal. So if I differentiate everything with respect to x, I should end up with another valid equation, right? What do I get on the left side using the chain rule if I differentiate with respect to x, not y? If I differentiate with respect to x. Well, there's two layers then, aren't there? At the outermost layer, I've just got hand squared. What's the derivative of hand squared? 2 hand. So I get 2y times, now we look inside. What's the derivative of y? Okay, the derivative of y with respect to y is 1. What's the derivative of y with respect to x? That's it, just dy dx, but our shorthand for that is y prime, isn't it? Y prime is just a shorthand way of saying dy dx. You see the trick? So if I just differentiate both sides with respect to x by the chain rule, every place I have a y, I'm going to end up getting, by the chain rule, the last link in that chain is going to be a y prime, isn't it? You guys have done stuff like this already. Without really even thinking about it, you've done a bunch of stuff like this. Oh, that's right. You've done stuff like that. In fact, we have a bunch of derivative rules that you already use this all the time. Like, for example, what if we have something like what's the derivative with respect to x of u to the n? N times
u to the n minus 1
times
u prime.
u prime. Yeah. What's the derivative with respect to x of e to the u? Okay. You've done stuff like that. Like, for example, if I gave you the problem, the derivative with respect to x of e to the x squared, you would tell me e to the x squared times 2x, correct? Okay, is that any different than saying the derivative with respect to x of something like y squared? No. I'm just going to do the derivative of y squared is just, instead of a y, instead of a u, I've got a y, right? So you told me it was n times u to the n minus 1. So this would equal 2 times y instead of u to the 2 minus 1 times, instead of a u prime, it's a y prime. You already know how to do this, right? This is already familiar territory, okay? So now what about the other side of the equation then? So that's what we got from the left side. What's the derivative of x with respect to x? 1, right? Well, solve that for y prime. Oh man, look at that. How easy is that? Right? Simple. Okay? Okay, so we already did that. So let's try this one again. You can do this, right? If I want to find dz dt, I'm differentiating both sides of the equation with respect to what? When I say I'm differentiating with respect to, I'm talking about the bottom of the derivative, right? I'm differentiating with respect to t, right? So on the left side, I get dz dt. What am I going to get on the right side? I'm just going to follow my rules. What kind of rule am I going to follow there? So product rule, right? So I'm going to get x times the derivative of y with respect to t. Well, what's that? That's just dy dt, right? Plus y times the derivative of x with respect to t. There's nothing I can do with that. It's just dx dt. It's the rate of change of x with respect to t. That's my answer. Okay. What about one like, okay, let's go back to, actually, I'm going to come back to this one later. Let's do this one instead. Let's do some more traditional problems first. Just got to hammer out some drill and practice on this, kind of get used to it. So here I've got, what does the equation of that look like, by the way?
It's just a straight
Don't
line.
listen.
No,
Well,
it's a circle, isn't it?
Circle.
It's a circle.
Oh.
With the radius of
So
2.
that's what we're, okay, never mind. I'm tired.
Okay. Isn't that just, did you get that? You've never done that before?
It's been a while.
Okay. That's fine, I get it. I mean, this stuff, it's out of context, that's no big deal. So it's a circle with a radius of 2, right? X squared plus y squared equals 2 squared?
Yes.
Yeah.
Okay. So we get a circle with a radius of 2. And we want to differentiate that. That's a relation, clearly, isn't it? It's not a function, non-function. But that's all right. The nice thing about implicit differentiation is it doesn't care, right? If we differentiate with respect to x, we're going to get y primes without having to solve explicitly for y. This would be a little bit tougher if I had to solve that thing for y first. I would get the equations of the top semicircle and the bottom semicircle separate, right? Okay. I mean, we could do this explicitly, but it would be harder and longer process. Now let's just do this implicitly. Let's implicitly differentiate with respect to x. So what am I going to get from each side of the equation? I'm going to differentiate term by term on the left. What is the derivative of x squared with respect to x? 2x, right? And you might be thinking, where's the u prime? Well, I get 2x, right? By the chain rule, I get 2x to the 1 times dx dx. Well, dx dx is just 1, right? So I am technically doing the chain rule. I just don't need to, right? Because I'm
1, 2x. 1 times.
right.
Yeah.
2x times 1, exactly.
Yeah.
And I never really have to worry about it if the variable of the function matches the variable of differentiation. I know that u prime is always going to be 1, right? So I just get a 2x. Now, what's the derivative of y squared with respect to x?
2y.
Ah, okay, I get my 2y y prime equals the derivative of 4 with respect to anything is 0. Okay? So if I solve that thing for y prime, I guess I could divide both sides by 2. I'm just going to subtract the x and divide by y. So don't I end up just getting y prime equals negative x over y? Okay? It might be uncomfortable here at first when you look at this. It doesn't seem right maybe to have y's in your answer, but you should expect that when you use implicit differentiation. How come it's necessary here? Not only is it something you got to live with, it's actually very valuable to us. Like if I want to find, for example, I want to find the slope of this relation. So find y prime when x equals 1. Why do I need both x's and y's there?
Because there's 2
Ah, look at the picture, right? You can already predict, look what's going to happen. When x equals 1, I'm going to get 2 different tangent lines, aren't I? That's not very good. I mean,
Yeah.
right? So I'm going to get 2 different slopes. I should, depending on which point of tangency I'm using. When x equals 1, if I plug 1 back into my original equation for x, I'm going to get, that's the same thing as saying y squared equals 3, right? And so y would equal plus or minus the square root of 3. So what do you think the coordinates are of that point of tangency?
1.
Square root of 3.
And what about this point of tangency?
1.
Okay. And when I'm using this point of tangency, well, now what's that going to give me for my derivative? at this point, I'm gonna get the slope equals -1 over the square root of 3. Everybody agree?
Yes.
What about down here? Yeah, I'm gonna get negative times 1 divided by negative the square root of 3, so I get 1 over the square root of 3. Right? Okay? How about that one? Okay, now, I want you to appreciate the difference. This isn't a very much harder problem for you to do right now. There are a few additional steps, not that bad. But this one we could have done, it might have taken us an extra 4 or 5 minutes to do this using an explicit process where we solve for y in terms of x first. Okay? I double dog dare you to solve that for y in terms of x.
No.
Good luck, right? It's not gonna happen. I mean, it may not even be possible, but if it were, that's several days of hard work probably, just getting the y by itself.
Really?
Yeah.
That's crazy.
Yeah. So, I mean, I just say no to explicit differentiation steps, right?
Just say no.
This is not a hard problem to do using implicit differentiation. If I'm going to implicitly differentiate with respect to x, that's no big deal. What do I get from this first term if I'm differentiating with respect to x?
4x.
4x. Okay, now this one we got to be a little bit more careful with, right? So I'm going to leave the 3 out front. I've got a product here then, right? I've got the product of x times y squared. If I'm differentiating with respect to x, I've got to use the product rule. Agreed?
Yeah.
So what am I going to get? X times
2y.
times
Y prime.
y prime. The y prime is going to be right. That's going to be right there. Plus y squared times 1. I don't even really need to write the 1, do I? I'm going to put it there just so you can see where we got it. Okay, so there's everything from that term.
Yeah.
Minus 2 times the derivative of x squared times y. So that's going to give me an x squared times
Y prime.
y prime plus y times 2x. I'm gonna run out of room, aren't I? Maybe not. Plus
Y.
equals
Zero.
0. Okay. Okay, that might look like a mess, but if I'm solving for y prime, the algebra is actually pretty easy, right? Notice that the y primes are all to what power?
1.
To 1, right? How come? Because it's the last link of the chain rule. We're just multiplying something that might be complicated by y prime. So if I want to solve for y prime, think about this process then. Let's go ahead and distribute the 3 and distribute the negative 2 and kind of rewrite this thing first. So I'm going to get 4x plus 3, plus, if I distribute the 3, I'm going to get a 6x, y prime plus 3y squared minus 2x squared y prime minus 2 times 2 is 4xy, right? Plus 12, oh boy, how did I not notice that a long time ago? What was that supposed to be? Minus 4xy plus 12y squared y prime equals 0. Well, what would the steps be to get y prime by itself then?
Well, you
Algebraically, what would you do?
move over the terms that don't have Y prime. and
But-
then divide.
Right, everybody agree? I'm just going to push all the non-y prime terms to the other side. And we'll walk through the steps step by step here. But I think once we've done this once, you can combine about 3 steps in your head here. And just do this really in one big step, which I encourage you to do. I know that's a little different for a math teacher, but I find that when you start to get into these higher levels of math, the more you can do stuff like that, the better you get at math. And pretty soon you won't make any mistakes doing that either. So let's, we'll keep the y prime terms on the left. 6xy, y prime minus 2x squared, y prime plus 12y squared, y prime equals negative 4x minus 3y squared plus 4xy.
Yes.
Factor out a y prime and just divide by everything that's left behind, right? So we're factoring out a y prime. Six xy minus 2x squared plus 12y squared equals, let's put the positive term first, 4xy minus 4x minus 3y squared. Just divide both sides by that factor and we're set, right? So we end up with y prime equals 4xy minus 4x minus 3y squared divided by 6xy minus 2x squared plus 12y squared. That's our answer. It looks terrible, but who cares, right? I mean, that's our answer. In fact, I want you to tell me now, if we were being smart about this, if I wanted to find the slope of the tangent line to the curve below at the point 2,1, did I even need to do all that, everything I did there? I mean, I could solve this algebraically in terms of x's and y's, and then plug in 2 for x and 1 for y. But what's easier to probably simplify, variables or numbers? Probably numbers, right? So really, even up here when we first got our derivative, I could have just plugged in 2 for x and 1 for y and gotten a bunch of terms that are easily combined because they're just numbers, right? You get that? Okay. This would be my answer if I was being explicitly asked to find the derivative in terms of x and y. Okay? What are we at here?
25.
Okay. Okay, let's do one trig one. Get through, well, this last one. Let me not get through this. Let's try that. So verify that the, we'll take, I'm not gonna do that. We'll assume that's correct. Skip part A. Part B, find an equation of the line T. How would I verify it? Plug it in, right? Yeah, plug it in. And it would, I mean, that was not that hard to do. If I plug in pi for y and pi squared over 2 for x, what's sine of pi?
0.
0. Right. So I'm going to get 0 plus 2, 2 times pi squared over 2 is just pi squared.
Yep.
Equals pi squared. We just verified it. True statement, right?
Yeah.
Okay. Part B. We got to differentiate. Now we need a y prime, don't we?
Yes.
So what's the derivative? We got to differentiate term by term. What's the derivative of sine y with respect to x?
Cosine of y.
Good, I get cosine, derivative of sine hand is cosine hand. So cosine hand times,
Y.
Y prime.
okay, plus derivative of 2x with respect to x, 2, equals derivative of y squared with respect to x,
2y.
Y prime.
okay? So then all I'm going to do is push the y prime terms to one side and the non-y prime terms to the other, right? So this time, in order to keep that as a positive 2, we'll leave the 2 on this side. On the other side, I'm going to get all the y prime terms. Let's combine 2 steps. On the other side, we're going to factor a y prime out from each term, but I would have had a 2y y prime minus a cosine y y prime, right? And so my answer then is just going to be y prime equals my 2 on the top divided by 2y minus cosine y. Agreed? And if I want to evaluate that at this point, well, I can do that. So y prime then is just going to equal 2 over 2y, so that's 2 pi, minus cosine of pi is just 1, right? So there's my slope, there's my point. I can find an equation of that line just by, slope-intercept form, right? Okay? Good? It's a good place to stop.